All right. So, good evening to you all. We are going to start in 2 minutes. So I shall be waiting like for 2 minutes, 2 more minutes for more people to join here. I think the audio quality is correct, fine, right? Sorry. So this morning we had some intermittent issues with our internet connection, so we couldn't start in the morning. So yeah. So we have actually delayed the session, and we are starting right now. So I think all of you got the information. All right. So actually today we are going to continue where we left off in the last class. Right. Again, right at the onset of the class, I should tell you that whenever you encounter any issue, whenever you have any difficulty understanding something, I say, please interrupt me and ask me a question. I'll be happy to answer your questions. Okay. Please post all your questions in the live chat. And again, at the end of the class, I shall be sending you all the handouts and a link to watch the recording of the video. Right. So with that said, post all your questions in the live chat. I'm constantly monitoring the live chat. So yeah. And so I am doing a live streaming through through a software called OBS. And with OBS, I encounter a delay of like 30 seconds, around 30 seconds. So whatever I say here right now will appear to you with a delay of 30 seconds. Okay, from my perspective to your perspective, right? So if I say something and if I teach something and you ask a question, then there is often a delay of like 30 seconds to 1 minute, right? So yes, so if you ask a question, I would be answering your question like with a small delay in between. Okay, that happens, and there is nothing we can do about it. Okay, and I have been giving you assignments, many assignments, right? I've been giving you many assignments, and what is happening is we are actually solving the assignments in the next class. For example, the assignment that I gave you in the last class, we shall actually be solving that assignment in this class, right? So you haven't done the assignment in the last class. Yes, the assignment I gave you in the last class, we shall be actually solving that problem in this class. So if you haven't attempted the assignment in the last class, so you actually completely missed the assignment. Okay, so so the window for solving and submitting the assignment would be, say if I give you an assignment in this class, okay, your job would be to solve the assignment and submit it to me, okay, before the next class, because oftentimes what happens is I solve the assignment problem in the next class. So that way, often the assignment I give you, I am the one actually who is solving the assignments. In any case, it has been decided that 60 marks will be for your end semester examination, and for the rest of the 40 marks, that will be entirely conducted as assignments and as per your attendance and class interactions. Okay, since we are taking classes through this online mode, okay, your interaction through this will be considered, will contribute to a part of the marks that you get out of 40 for that part. So I think I cleared that up. So I would request you to submit the assignment, each of the assignments I give you, and these are very small assignments, right? I don't give you a long and complicated assignment. In any case, try solving the problems I give you promptly. Okay, by that day, that will be the best case scenario, right? You don't have to do it in a very professional way. Okay, you just have to attempt solving that problem. Okay, and this is again a pedagogical way of actually learning things, because if I don't ask you to, do something after learning something, you would never learn anything, right? Human retention capability is only 5% if you just listen. Okay, for example, if I teach you and if I am teaching you and you are just listening to me, okay, then your retention you shall be only retaining 5% of what I teach. Okay, but that 5% immediately jumps to about 70% if you try to do something with that knowledge, and that retention jumps to 90% or maybe even 100% if you try to teach that thing. Okay, so literally teaching is quite literally the best way of learning. Okay, with that said, I shall start the class right now. Okay, so I hope more people to join. Anyway, in any case, let's start our discussion today. So if you recall, And if you encounter any difficulty regarding the video quality, audio quality, or anything, please feel free to tell me. Okay, because kind of I am a one-man army here. For example, I am controlling the live stream, I am checking the live chat, and I am also writing here. So yes, I am monitoring two things all at the same time. I mean, more than two things all at the same time, right? So with that said, we're actually solving a few. Okay, cats are interrupting. Okay, we are trying to solve a few problems on Fourier transform, right? So actually we ended up to this point, right? We calculated the Fourier transform of 1, right? So right, we calculated the Fourier transform of these things and we ended at this 1. And we also discussed something called the principle of duality, right? So this is going to be one of the last few classes on Fourier transform, right? And on the next class we shall actually study different properties of Fourier transform. Maybe that will continue to the next classes. So there will be 2 more classes on properties of Fourier transform, and then we shall learn how we actually use this knowledge in analyzing systems, analyzing signals, and how they interact, how systems interact with signals, right? So we are going to learn those. But in any case, today we are going to just solve a few more problems that we left pending in our last class. So these are the problems, and these are very cherry-picked problems. For example, these are quite what should I say, if you open any book, okay, and if you recall, I recommended 2 books to you. One was by Oppenheim, Wilsky and Nawab, Signals and Systems by Oppenheim, Wilsky and Nawab. That was one of the books. So let me just once again write it here. Okay, Oppenheim, Wilsky and Nawab. So that's literally the best book available on signals and systems. And if you want a book by an Indian author, so you can always go through these books. Okay, these are for the portions we have been talking about so far, right? Okay, for example, this by T.K. Rawat. Okay, this is published by Oxford Publishers. This is published by PHI. So this is by Oxford. So yes, and there is Ramesh Babu, right? So these books are there. So I'm personally following this book, and I'm giving you a lecture plan where you actually get which portions of the book I'm actually following. So the idea is that if you open any book that has on signals and systems that has a treatment on Fourier series, Fourier transform, you will see these are the problems that the book will actually solve for you. So these are pretty much standard problems that we actually solve. So let's start with this today, right? We did discuss plenty of things, plenty of ideas. We covered plenty of ideas that back in that day. So let's start with this: e to the power j omega naught t. All right, and we shall solve this problem today. So right, so we are calculating the Fourier transform of now this is the signal e to the power j omega naught t, right? And as electrical engineers, you people are supposed to be quite familiar with this kind of signals, right? This is just a representation of a complex sinusoid, right? This is representative of a sinusoid that has an amplitude of 1 RMS amplitude, for example, the amplitude of 1, okay, peak amplitude of 1, and a phase angle of 0, right? Something like that, right? So for example, while discussing AC, alternating current circuits, we often express our signals in this way. Sometimes while discussing AC circuits, specifically the sinusoidal steady state analysis for, solving AC circuits, anyway, in your circuit theory classes or maybe in your basic electrical engineering classes, you studied that we often write signals, AC power signals, for example, current signals, voltage signals, whatever. We express those as quantities like this: V angle theta, I angle theta, right? We have seen those expressions, right? And what are those? This V is representative of the RMS value for that particular scenario, and this theta is the phase angle, right? And of course, if I am writing that, then I'm calling that particular voltage quantity or the current quantities, for example, a phasor quantity, right? So we express that with a overline or an underline, right? So something like that. So maybe that's my voltage phasor quantity, right? Something like that. So this V is representative of the RMS voltage, and theta is representative of the relative phase, okay, with respect to the reference phasor I'm considering, something like that, right? So again, this, if I have something like this, then this can also be written as V root 2 e to the power j omega naught t plus theta, something like that. But theta is this phase angle, okay? For example, this theta is the phase angle here, and this is representative of the angular frequency of the signal, which is 2 pi into f. In India, the power frequency is 50 hertz, so f would be 50 here. So that would be 2 pi into 50, like 314 radian per second, something like that. So that's the phasor representation of a signal. So this, what I'm writing here, is nothing but the phasor representation of a sinusoidal signal, right? Sinusoidal voltage or current or something like that. Right. So let's try figuring out the Fourier transform of this. But again, right off the bat, you understand that this is a periodic signal. This is not an aperiodic signal, right? This is indeed a periodic signal because this is representative of a sinusoid. So we said that we do Fourier transform when the signal is aperiodic, but that's a generalization. So since Fourier transform is applicable for aperiodic signals, it is also applicable for periodic signals. All right. This signal is periodic, and this signal has an angular frequency of omega naught radian per second. Frequency of omega naught radian per second. So right there, like something like that, right? So let's calculate the Fourier transform of this. So therefore, x omega, okay. So we are doing it the standard definition way, right? So yeah, we have to do this integration on this signal. Right, so we have that, right? So with that said, if I have this, and let's try putting that value, because I mean it's not difficult to understand that it is going to be a simple integration here. So it is e to the power j omega naught t, and I'm not considering an expression where I have plus phi, because that would be a constant term just multiplied with everything, right? So e to the power j omega naught t plus phi or theta, whatever I have, if I have something like that here, that simply results into e to the power j omega naught t into e to the power j theta or j phi. That just turns out as a product, right? So you multiply everything with that. Nothing happens with that because that becomes a constant term. Okay, there is no time involved here. Anyway, so right. So with that said, I have this. I have this. This is the signal we are talking about, and into e to the power minus j omega t. So one thing to note here though are these quantities omega naught and omega. Try to understand the distinction between these two. Omega naught is a constant. The distinction is that omega naught here is a constant, okay, pertaining to the particular frequency we have for the sinusoid. For example, we are in India, for example, so for us f is 50 hertz. So omega naught would be 314 approximately radian per second. So omega naught is a constant, but omega is a variable for the Fourier transform, right? So omega is a variable. So try to understand that. Okay. So this comes from, this omega is from Fourier transform, the Fourier transform expression, and this is the constant term that we have with the signal, right? So this is a omega naught radian per second sinusoid. That's the frequency of the particular sinusoid. So if I integrate, before I can integrate these, so I have to first, take care of the exponents. So let's take j common. So I would have omega naught minus omega into t and dt. Okay, so right, I don't think there is an issue with this, right? All right, so now do tell me, what is the integration? What is the integration? So if I ask you what is the integration, try to understand what happens. Okay, if I ask you what is the integration of this, again we are encountering the same issue we encountered earlier while solving the problem for this. While calculating the Fourier transform for 1, we encountered an issue where we actually could not integrate this, right? We have a situation like that. While calculating the Fourier transform of 1, if you recall our last class, we encountered a situation that appeared to be somewhat like this, right? If you recall, right? And we now don't really know what to do with this, because if we have e to the power minus j omega t, something like that, an expression like that, right? So yes, we don't have any constant term added to this, right? So I'm not entirely sure what to do now, right? Do you understand my problem here? Okay, if I just naively integrate this, I would get e to the power j omega naught minus omega into t by omega naught minus omega. So j omega naught minus omega, and I have these limits. But try to understand that I'm not entirely sure what to do here, because this is like cos omega naught minus omega t plus j sine omega naught minus omega. So basically, let me write it so that you actually get the idea properly. So this is cos omega naught minus omega t plus j sine omega naught plus omega, sorry, minus omega t divided by j omega naught minus omega, right? And I know that this is bounded, right? Cos cannot go beyond +1 and -1. Sine similarly cannot go beyond +1 and -1. But yeah, what if I put infinity? I don't have any particular value for this, right? So this method of doing this is not suitable for us, because this is not how you proceed with this integration. This particular integration cannot be proceeded this way. This will have to be dealt in a complex integration fashion. So this method that we just did is actually wrong. This is wrong. Again, just to show you what we have. Okay, this is a wrong method, right? So again, can anybody tell me what is the correct way of doing it? Of course, the correct way of doing it would be the way we used for calculating the Fourier transform for 1. Right? You have that. You can recall that, right? So while calculating the Fourier transform of 1, what did we exactly do? We used the principle of duality. We try to figure out what is the quantity for which the Fourier transform is 1, and then we applied the principle of duality to calculate the Fourier transform of 1. Okay, so using principle of duality, we always try to figure out what is the quantity for which the Fourier transform is this one. Okay, so we wanted to calculate the Fourier transform of 1, so you first figured out what is the Fourier transform, what is the quantity whose Fourier transform is 1, right? So of course we already knew that the Fourier transform of delta t was equal to 1, right? So from that knowledge, we use the principle of duality, yes, and we use the principle of duality to calculate the Fourier transform of 1. So this is what we are going to do right now. So we are trying to figure out in this discussion right now, we are trying to figure out what is the quantity. So this is not the correct way. Again, this is not the correct way of doing it. So we are trying to figure out what is the quantity for which the Fourier transform is this. Okay. So let me tell you what is the quantity for which the Fourier transform is this, right? So let me start, because I know already how this integration works, and you will soon realize that. So now let's see how we proceed with this now. But let us consider the Fourier transform So I'm asking you to calculate the Fourier transform of something right now, okay? And this will be quite evident momentarily why I am asking you to do this. So I'm asking you to calculate the Fourier transform of delta t minus a, for example. I'm asking you to calculate the Fourier transform delta t minus a. The question is, what is delta t minus a? What is delta t minus a? Delta t minus a is a delayed unit impulse, okay, right? So if I draw delta t minus a, which is nothing but a delayed unit impulse. So delta t minus a would be nothing but a delayed unit impulse, right? Right. So that's my delta t minus a, and this time is of course a. This time is 0, right? Something like that. So it's a delayed unit impulse, right? So I'm asking you to calculate the Fourier transform of delayed unit impulse, and this will have significant correlation with what we are trying to do. Okay, so let's calculate that. Okay, so let's calculate the Fourier transform of this, right? So how do I calculate the Fourier transform of this? So of course this is the Fourier transform of delta t minus a, and if I do that, then what am I going to do? I'm going to integrate from minus infinity to infinity, and of course delta t minus a, and for Fourier transform I have this, right? Now of course doing an integration with delta is pretty easy, right? We already know that is a property of Dirac delta or unit impulse. Recall the property. We did this in an earlier class. Recall this property of Dirac delta or unit impulse, whatever you want to call it. This is one of the important properties, okay, of unit impulse, which is delta t minus a ft dt. This integration is fa. Again, we proved this in one of our physical classes, okay, but this is again very similar to what we did earlier, what we used earlier, that delta t into ft dt integration from minus infinity to infinity was f0. Now this is fa when we have delta t minus a, for example. The only condition is that ft will have to be continuous at t equal to a, right? That's the condition. Again, we are considering continuous signals, so this signal we are dealing with is a continuous signal, right? So yeah, that's one of the properties, right? So if I use this property, okay, of unit impulse and try to integrate this, try to look at this one with this property, if I try to look at this one, what do I have? I have delta t minus a, and then we have, this is like ft, this thing, e to the power minus j omega t, that's like ft, right? So with this property, if I apply that here, the answer would be simply fa, right? Now what is ft? Ft is e to the power minus j omega t, right? You got that, right? What is ft? It's minus e to the power j omega t. Then what is fa? That's going to be e to the power minus j omega a, right? So that's going to be, so that's going to be e to the power minus j omega a, right? All right. Right, I think this is easily understandable, right? There is no issue with this because we are not doing any complicated integration here. Yeah, we have e to the power minus j omega a. Right. Again, these properties of when discussing this, I told you that these properties of unit impulse are pretty important, pretty regularly used everywhere. Okay, so we have just used this. So what we have just discussed, we have discussed that the Fourier transform of delayed impulse. So this is how we, often write things. Okay, is e to the power minus j omega a. That's the Fourier transform of delayed impulse, right? There is no problem with that. Then from this, tell me if I can write something like this. What if I replace a with minus a? So this is like an advanced impulse, right? Left shifted impulse. Okay, if I shift the impulse left, okay, so it's a left shifted impulse. Okay, so of course I'm replacing that. So do tell me if this is correct, right? So from this we can always infer this, right? Of course, understandably, that's not an issue, right? Right. So yeah, do tell me if you understand this. If you don't understand this, rather. Right. here we are going to use the principle of duality. Okay. So try to understand, this is my xt and this is giving me x omega. So I know that the Fourier transform of delta t plus a would be e to the power j omega a. That's x omega, right? So from the principle of duality, we know that the Fourier transform of capital xt is going to be 2 pi x of minus omega. So this is from duality. Right. Yes, so if you understood, please confirm. If you don't understand something, please interrupt me and ask me a question. So that's the principle of duality, right? So for this particular scenario, xt is, this small xt is delta t plus a, and we have this x omega then. That's the Fourier transform. So now we are calculating the Fourier transform of capital xt, right? So we are saying for this particular example, xt is this and x omega is this, right? If capital X omega is e to the power j omega a, okay, e to the power j omega a, then what is capital xt? What is this? What is this? So if capital X omega is e to the power j omega a, then what is capital xt? So you're just replacing omega with t, right? That's e to the power jta, right? Jta, right? Like that. There is no problem with that. And from the principle of duality, I know that the Fourier transform would be 2 pi, okay, x of minus omega. And again, what is xt? Xt is delta t plus a. Then question is, what is x minus omega? We just have to replace. So this is xt again. Look at this one. This is xt. And how do I calculate x minus omega? Just replace t with minus omega. So we have delta minus omega plus a. And again, look carefully here. We just replaced t with minus omega. That's how we have the Fourier transform of that. I don't think there is any issue with this. There is any problem here, right? That's simple to understand. All right. So this is e to the power, this is the Fourier transform of e to the power jta, which is nothing but e to the power jat. Of course, jta and jat, they are the same, right? And that's 2 pi delta minus omega plus a. All right. And this a is nothing but a random constant, right? Some constant. Okay. This a is the amount of delay that happened in delta, right? So that's a constant. So I can always call it anything I want because that's not a variable, it's a constant, right? Okay. Right? I can change the name. I can, instead of writing a, I can write b, I can write c, I can write whatever. I can write omega naught. So it's going to be e to the power j omega naught t. So I just replaced a with another name. So omega naught is nothing but a new name for this. That's going to be 2 pi delta, right, minus omega, and instead of a, I'm writing omega naught. All right. So we have just solved the Fourier transform for e to the power j omega naught t from the principle of duality. We could not do it without knowing complex integration quite well. So yeah, we avoided complex integration by means of using principle of duality for Fourier transforms. Right. So our original objective was to calculate the Fourier transform of e to the power j omega naught t, which is representative of a complex sinusoids, which we often use in regular cases. So we have just calculated the Fourier transform of that by means of the principle of duality, right? But we are not done yet. Okay. Before we are done, we have to recall another property of unit impulse. Okay. Recall this property of unit impulse. Recall that, again, we proved all of these properties in our earlier classes, that this happens. This is one of the properties, right? All right. So therefore, what do I have? If I have this property in my mind, then I know that the Fourier transform of e to the power j omega naught t, Fourier transform of e to the power j omega naught t is 2 pi delta minus omega naught. I can take the minus sign common, so minus 1 common out of these. Omega naught minus omega naught, something like that. So we essentially have a minus 1 common out of everything, right? From here, right? And from this we know this property of unit impulse, I know this minus 1 can go outside just like this one, okay, and it will become 1 by this because of this property, and we have delta omega minus omega naught. And again, you can treat that with the idea that delta is an even function, right? We established that in the last class. So I have 2 pi delta omega minus omega naught. So that's the final answer, right? Our final answer is that the Fourier transform of e to the power j omega naught t is 2 pi delta omega minus omega naught. All right. So if you have understood that, right? So let me draw the frequency spectrum, frequency domain expression plot, right? Frequency spectrum. So this is a pure sinusoid, right? So this is a complex, rather complex sinusoid. What is this? A complex sinusoid, right? Complex phasor quantity, right? Right? Complex phasor quantity. So basically a sinusoid of frequency omega naught radian per second, right? That is what it is, right? So what is the Fourier transform? What does the Fourier transform look like? So if I draw this, what is this? This is in the frequency domain, right? So let me just draw that. Try to understand this. This is omega, and this is mod x omega. If you take a mod on this, nothing changes, right? So in the frequency domain, what does this one look like? In the frequency domain, what does this one look like? In the frequency domain, try to understand that this is a delayed impulse, right? Right? And this is a delayed impulse that happens to be appearing at omega equal to omega naught, and this has an area of 2 pi. Of course, that is representative of the area under the impulse, right? So it's an impulse of magnitude of 2 pi. What is this representative of, right? What is this really representative of? In the Fourier domain, or for example in the frequency domain here, this is representing the fact that this signal consists of a single sinusoid, right? The Fourier transform immediately tells me that this signal comprises of a single sinusoid. And what is the frequency of the sinusoid? The frequency of the particular sinusoid is omega naught, and which is quite in agreement with what we already know about the signal, right? This is a single sinusoid of frequency omega naught, and that is what it gives me. Okay, this gives me that, okay, this is a sinusoid, and this gives me the composition of the signal. So the Fourier transform tells me, okay, this signal that we just calculated the Fourier transform of has only one sinusoid, and that sinusoid happens to be at a frequency of omega naught radian per second, right? And this is the relative amplitude of that particular sinusoid. Okay, so yes, so with a Fourier transform, this is understandable. This is understood that with the Fourier transform, we can actually figure out the particular frequencies, particular frequency components present in the signal. Okay, someone asks, can you repeat the last part? Repeat this portion. So with this, we have this property, right? So from this, we can just take the minus sign common out of this, right? So if you take the minus sign common, okay, and then apply this property here, I would have 1 by minus 1 mod minus 1 outside like that. So we have taken minus 1 outside this, right? And from that we just have this, right? And so this is the Fourier transform of this complex sinusoid, right? And this Fourier transform tells me that this is comprising of a single sinusoid of frequency omega naught and a relative amplitude of 2 pi. So yes, I think this is quite simple to, not very difficult to understand. Please ask me if you haven't understood this. Right? And often while solving, calculating the Fourier transform of different things, we use our prior knowledge on things, right? We often use the Fourier transform of the things that we already calculated. Right? So we're going to soon see that. With that said, if you have any difficulty understanding, please ask me, let me know. And if you have understood this already, just let me know again, so that I can proceed. If you have any query, please let me know if you have understood this. So please confirm if you have understood this. All right. So you are asking, there is a huge time gap in that delivering any message to me. Okay, that might be an internet issue, right? That might be an internet issue. So please try to follow along then. Okay, and post your questions, and if you have any query regarding anything, okay, please point that out to me. Okay, please point that particular thing out to me. Instead of saying, yes, please, sir, please repeat, instead of saying that, say, sir, please repeat how this integration worked or something like that. Okay, please write a few more lines so that I actually understand what you are asking for. Okay. I know there is a gap of like 30 seconds to 1 minute, something like that. I know that already. And there is nothing we can do about it. Okay. Okay. That is the time the stream transition and stream compression, everything actually takes. Anyway, so if that is understood, then let's go back and the list of problems we are going to solve today. Okay. So the next problem we are going to solve is the Fourier transform of cos omega naught t, right? Cos omega naught t is a pure sinusoid, right? Or rather cosinusoid of frequency omega naught, right? Right. So that's our problem number 6. So our signal is cos omega naught t, right? So it's a pure cosinusoid of omega naught t, this frequency. Right? So question is, what is the Fourier transform of this? So we are calculating the Fourier transform of cos omega naught t. So again, instead of jumping into the integration and doing everything like that, if I do everything like that, we will again soon encounter that our standard real integration, tricks on real integration does not work here, because this will again turn out to be a complex integration where there is a limit, and the limits, if I apply, they do not converge to anything. We again have a problem with this, right? So now instead of going back and trying to figure out how to apply principle of duality, in this scenario, in this example, we shall try to figure out what we can use from the things that we derived already, right? What are the information that we can use from the things that we derived already, right? So what we already know is that the cos theta is expressible. We discussed this in the last class, that cos theta using Euler's theorem is expressible as e to the power j omega naught t plus e to the power minus j omega naught t divided by 2. That is how it is expressible, okay, as complex exponents, complex exponents, right? So these are complex exponentials, and this is how we can express cosinusoids and sinusoids. For sine, if this was sine, then there would be a minus sign here, and I would, instead of having 2 here, I would have 2j, right? We discussed that in the last class, hopefully. Not the last class, last one before the last class, right? Yeah. So with that said, now we have to understand that the Fourier transform is just nothing but an integration on something, right? And that integration term itself is a linear operation, right? Integration. So the idea is that integration over the sum of two function is nothing but the integration sum of the integrations. So what I mean is that integration on, say for example, fx dx plus integration on gx dx is nothing but integration on fx plus gx dx, right? We know that. And since Fourier transform is nothing but an integration of like that, Fourier transform itself is a linear operation, right? So this can be split accordingly, right? So with that said, this is nothing but the Fourier transform of two individual terms. I can bring the half outside, right? And this is nothing but the Fourier transform of two individual terms, e to the power j omega naught t, okay, plus Fourier transform of e to the power minus j omega naught t, right? All right, right? So there is no problem with that, right? So we just have split everything like that, because Fourier transform itself is just an integration, so it can be split like that, right? So moments ago we actually calculated the Fourier transform of this e to the power j omega naught t, right? So we calculated the Fourier transform of e to the power j omega naught t, and this turned out to be 2 pi delta omega minus omega naught. So I am just putting that what we derived moments ago. So half, and the Fourier transform of this okay. Let me, before I can actually proceed with this, let me tell you the linearity property of Fourier transform. That would be useful for you to understand, right? Okay, let's hold on to this for a moment. Okay, linearity of Fourier transform. Okay, so let's say we are trying to figure out the Fourier transform of we know that the Fourier transform of xt is x omega, right? So by definition, what do I have? I have x omega as integration from minus infinity to infinity xt e to the power minus j omega t dt. That's from the definition, right? Now what if I multiply k on both sides? K on both sides, where k is just a constant, okay, real constant, real number, a real constant, or maybe a complex constant as well. So if I multiply k on both sides, I have k into x omega, and here if I multiply that same thing here, I have k outside like that, right? So where k is a constant, complex constant, right? Any constant number, right? And this can go inside because that's a constant irrespective of omega or t, what irrespective of t, right? So it can go outside, inside. right? I can write that, right? So do tell me if this is okay, right? So what have we just discovered? We have discovered that the Fourier, so this is what is this? This is the Fourier transform of k into this, right? Then I can say that the Fourier transform of k into xt would be k into x omega. That's the homogeneity property, right? For linearity, it has to be homogeneous and additive, right? Homogeneity and additivity must be satisfied. So this is the homogeneity property, right? Yeah, the k basically tells you this. Try to understand. Here I'm saying that if this is holding true, then this also holds true, then which means these are all true. Try to understand, these are all true. For example, so okay, moments ago I told you example, so let's write down examples, right? Moments ago I told you that the Fourier transform, so what did we know? For example, we know that the Fourier transform of e to the power j omega naught t, what is the Fourier transform of that? We moments ago realized that the Fourier transform of this is this. Now this k tells you that the Fourier transform of, say for example, 5 e to the power j omega naught t is nothing but 5 into this entire thing, right? Of course, why not, right? That is what it tells me, right? That's the homogeneity property, right? This is the homogeneity of Fourier transform. So in order for Fourier transform to be linear, it must satisfy homogeneity and superposition, right? So we are checking for homogeneity. And let's now check for additivity or superposition. Let's check for additivity. Yeah, I think you people got it, but let me still prove it, because that will save me from proving it once again while discussing the property of Fourier transform, because we were actually going to prove this in our next class, but let's do that here. Okay, so let's say the Fourier transform of xt is, let's say the Fourier transform of xt is x omega, right? And say Fourier transform of yt is y omega, right? So my question is, what is the Fourier transform of xt plus yt? My question is, what is the Fourier transform of xt plus yt? What is the Fourier transform of that? So let's do that, calculate that. So Fourier transform of xt plus yt, right? So we are trying to calculate that Fourier transform of xt plus yt. And if I do that by means of calculating the integral here, of course, that's going to be from this to this integration, right? So xt plus yt into e to the power minus j omega t dt, right? So, and that gives you, for example, integration from minus infinity to infinity, xt e to the power minus j omega t dt, plus, you people already would agree with this, right? But what is this? This is the Fourier transform of xt, so that's x omega. And what is this? This is the Fourier transform of yt, so it's y omega. So what have we just discovered? That if x omega is the Fourier transform of xt and y omega is the Fourier transform of yt, then the Fourier transform of xt plus yt is x omega plus y omega, right? Since we have proved homogeneity and additivity separately, now we can say this. So linearity is homogeneity plus additivity, right? So we can now say that, rather, instead of writing that, therefore linearity tells me, what does linearity tell me? Linearity tells me this, that if the Fourier transform of xt is x omega and the Fourier transform of yt is y omega, then the Fourier transform of axt plus byt is going to be ax omega plus by omega, right? And this can be extended to as many terms as you want, right? So if you have x, y, z or something like that, whatever, does not matter, right? So that's the linearity of Fourier transform. I think I got that point through to you, right? So with that said, let's go back. I believe this is understood, right? This wasn't difficult to understand. Let's go back, and I think this is understood how we got the half outside, how we separated these two individual terms. Because yes, if I take sum of two functions and try to calculate the Fourier transform of them, I can calculate individual Fourier transform and sum them up. But remember, this does not apply for multiplication, right? Linearity does not give you, the linearity property for multiplication. Multiplication is not linear, right? Addition is linear, for example, here. Understandable, right? So that's half outside. And we already know the Fourier transform of individual terms like that. So what is the Fourier transform here? This Fourier transform for this particular term is 2 pi delta omega minus omega naught, right? We calculated that moments ago, right? Right? So that's the Fourier transform of this. So e to the power j omega naught t, that's 2 pi delta omega minus omega naught. And for this, the Fourier transform, of course, if the Fourier transform of e to the power j omega naught t is 2 pi delta omega minus omega naught, then of course the Fourier transform of e to the power minus j omega naught t is this when we replace omega naught with minus omega naught, right? When we replace omega naught with minus omega naught. So yes, there is no problem with that. So the same answer, and we just replace omega naught with minus omega naught. So it's going to be 2 pi delta omega plus omega naught, right? Yeah, same thing, right? And we can take 2 pi outside and divide it with pi. So I have pi plus delta omega minus omega naught plus delta omega plus omega naught, right? I think you people got this, right? So with that said, this is pi delta omega minus omega naught, and this is pi delta omega plus omega naught, right? So my question is, how would this look like if I draw it? If I draw this, so this is the Fourier transform of, so therefore the Fourier transform of cos omega naught t was pi delta omega minus omega naught plus pi delta omega plus omega naught. So if I draw this, so this is a pure cosinusoid, right? It's a pure cosinusoid. And what if I just draw the Fourier transform here? So that's omega, okay, and that's mod of that. Again, there is no complex term, so the mod will be itself, for example. There is no problem with that. With the negative, we don't have even a negative sign here. So yeah, these are all positive deltas, right? So this is a delayed impulse that happens at omega naught, and this is an advanced impulse that happens at minus omega naught. So if I draw them, the result, so resulting frequency response, we often call this a frequency response. Again, we shall elaborate these terms later on. But in the frequency domain, the Fourier plot of the Fourier transform kind of looks like this. Right? Right, absolutely. So with this is at omega naught and this is at minus omega naught. This is an impulse, this is also an impulse. No, we cannot take delta common because delta is the name of the function, right? It's name of the function, right? You got the point, right? Delta is the name of the function, name of a function. You cannot take that common, right? Delta is not multiplied, right? Delta is the name of a function. This is not delta multiplied with omega plus omega naught. Delta is the name of a function. It's delta t, right? Delta omega, for example, right? It's the name of a function. You cannot take that name common, right? Right? If you have sine a plus sine b, do you write sine a plus b? You don't, right? Because you cannot take the name of a function common like that, right? Okay, with that said, with that said, what is this? What is the that area under this is pi, the area under this is pi. So what does this imply? What is this? This is a pure sinusoid, right? It's a pure cosinusoid rather. Pure cosinusoid. Okay, of frequency omega naught radian per second, right? It's a pure sinusoid of frequency omega naught radian per second. But what does the Fourier transform tell me? Fourier transform tells me that it actually has two components. The Fourier transform somehow tells me that it has two components. What components? The Fourier transform surprisingly tells me that this simple cosinusoid that had a single frequency of omega naught for us has two components. What two components? It tells me that it can have a frequency of omega naught and an amplitude of pi, and it can have a frequency of minus omega naught and an amplitude of pi. Let that sink in. Fourier transform told me something that we might have already missed somehow. Okay, what am I talking about? Okay, so Fourier transform told me something that we probably have missed. Okay, right. So what did we miss here, for example? Okay, in this scenario, try to understand we missed something very important, right? Again, let's go back and let me tell you, what is this? This is a representative of a pure sinusoid of frequency omega naught, right? What is this? This is a pure sinusoid of frequency minus omega naught, right? And what is the relative amplitude? Relative amplitude pi, relative amplitude pi, right? You got that, right? But what is Fourier transform telling me? Fourier transform is telling me that this signal is comprising of two different sinusoids. One sinusoid of frequency plus omega naught, one sinusoid of frequency minus omega naught, right? Why is that so? That is so because Fourier transform tells me everything that's ever possible about the signal. And what am I talking about here? I'm talking about this. Try to understand that cos is an even function, right? So calculating Fourier transform of cos omega t is identical to calculating Fourier transform of this. So for the Fourier operation or Fourier transform operation, it does not really know whether the signal I'm talking about has a frequency of plus omega naught or a minus omega naught, because those would both appear to be the same as far as the Fourier transform operation is concerned. But the operation is so elegant and so nicely designed that it can still distinguish and tell you all the possibilities. It is telling you that the signal might have a omega naught frequency, okay, sinusoid of omega naught frequency, and it might also have a sinusoid of minus omega naught frequency. But as a matter of fact, it's telling you that it possibly has both. It possibly has a frequency of omega naught and a frequency of minus omega naught. How? This is how. While doing the Fourier transform, the Fourier operator under the hood does this. Under the hood, it writes cos omega naught t as two different things. Under the hood, let me just draw it in a different color. Under the hood, it considers cos omega naught t as half cos omega naught t plus half cos omega naught t, and this one it considers to be a positive frequency cosinusoid, and this one it considers a negative frequency cosinusoid, because these are the same, right, as far as the cosine is considered, right? So it's kind of considering a composition of a sinusoid or cosinusoid with a positive frequency and a cosinusoid with a negative frequency, because this is quite possible, right? This is quite possible that this is how we got up to this point, right? So it tells you that. Okay, and this half can assure you about something. Let me go back. If I go back, if I had a pure sinusoid or rather a pure complex phasor quantity, see, it specifically told me this complex phasor quantity is unambiguous in nature, right? I cannot just put minus omega and tell you that it's the same, right? I cannot say that. So here it told you that it had a single frequency component, single sinusoidal component of frequency omega naught. Okay, but the relative amplitude was 2 pi. The relative amplitude was 2 pi here. But here, since this is kind of confused, okay, this now tells you that it has two sinusoidal components, one at plus omega naught frequency, one at minus omega naught frequency. But since it is telling you it has two sinusoidal components, it is giving them both half amplitude. Okay, so it is giving half relative amplitude to each. Instead of saying 2 pi for each, it is saying pi for each, right? And explain the cost part you just said. Yeah, so cosinusoid, for example, right? I could, instead of doing the entire thing, I could have done the entire thing for cos of minus omega naught t, right? Right? Tell me, the answer would have been identical. Try to understand, the answer would have been identical because, for example, cos of 2t is identical to cos of minus 2t, right? May I ask you, what is the frequency of this signal, cos of 2t? You say 2 radian per second. What is the frequency of cos of minus 2t? You say minus 2 radian per second, right? But will you be able to distinguish these two signals? No, you won't be able to distinguish these two signals because cos 2t will appear to be identical to cos of minus 2t, right? Right? They will appear to be identical in nature. Since they would appear to be identical in nature, Fourier transform is giving you the opportunity to distinguish them in a sense, right? Fourier transform is telling you that, okay, instead of considering this to be just the positive frequency, I am considering, this is what the Fourier transform is telling you. The Fourier transform is telling you, instead of considering this to be just the positive frequency, I am also considering 50%, I'm considering 50% positive frequency, 50% negative frequency. And how is that possible? This is possible by the fact that cos of minus omega t is nothing but cos omega t. So this is what we can write, right? So the Fourier transform specifically tells you something that you might have missed by looking at the signal, right? Because this signal itself can be expressed in two ways. Okay, omega naught can be 2 radian per second, can be minus 2 radian per second. It can be 10 radian per second, it can be minus 10 radian per second. And who is there to guarantee that it's going to be positive frequency, right? So Fourier transform here is kind of not taking any chance with this. It is considering 50% positive frequency, 50% negative frequency. And with that, it is telling you that it is comprised of two sinusoids. Instead of saying one sinusoid, it is saying it is comprised of two sinusoids. One of positive omega naught frequency and one of minus omega naught frequency, right? One at frequency of positive omega naught, one at frequency of negative omega naught. So it is comprised of two sinusoids from the perspective of the Fourier transform. But it is giving each of the sinusoid half, okay, half amplitude. Because if you look carefully at the previous example, when it was able to discern the particular frequency unambiguously, okay, it gave it the full possible amplitude. It gave it an amplitude of 2 pi. But here, Fourier transform is telling me that each of the component has an amplitude of pi, relative amplitude of pi. So it is actually what it is doing under the hood. It is dividing the cosinusoids, okay, into two separate parts, okay, one with a positive frequency, one with a negative frequency. And with that, it is actually telling you that it is actually having two sinusoids, one at positive frequency, one at negative frequency, right? Because there is nothing that guarantees that this omega is positive, omega naught is positive, right? And you won't be able to distinguish between cos omega naught t and cos minus omega naught t, right? If I just give you a plot. But if I give you the phase, you shall be able to distinguish them. So we shall talk about phase differently in different class, right? So what is the thing that can let me distinguish between negative frequencies and positive frequencies? The answer is the phase. Okay, we shall later on understand that, later on learn that. But for the moment, try to understand that Fourier transform takes care of every possible scenarios, right? And that's the beauty of Fourier transform. It gives you all the insight that you can even have about the signal. Okay. So even if you didn't consider the fact that the frequency could be negative, Fourier transform did that for you. Okay. It did not assume anything, right? It did not assume that it has a positive frequency, right? It did that for you automatically. So that's how this really works here. So with that said, let's go back. Okay. Of course, that was our problem number 6. Of course, I believe the problem number 7 would be a homework for you, because that gives you this is going to be a homework for you. This is going to be an assignment homework. Find the Fourier transform of course, sine omega naught t. It's a pure sinusoid of frequency omega naught t. So you can follow the example and accordingly proceed with that. And again, if you are unable to do this, we shall of course do that at a later class. So don't worry. Okay, what was the next example? Example number 9. Yeah, rectangular pulse, right? And again, we are going to take as many classes as needed to clear up these ideas, because you need to have concrete idea of Fourier transform in order to proceed further, right? So if you become an electrical engineer without understanding Fourier transform, it's kind of a bad thing. Okay, so let's do that. Okay, so go to this this example. Okay, a rectangular. Okay, before I actually solve this 8th example, let's do the 9th and 10th, because I think those will be easier for us to do. Okay, so signum function and unit step. Let's do that. Do those first. Okay, 8. So we are going to do that later. Okay. Yeah, do this, solve the problems and mail it to me. Okay, I want to see you attempting the problem. That's the important part here. Okay, you try attempting the problem based on the knowledge we gathered in our classes, right? I think I should turn the webcam off. All right. So with that said, okay, so we are trying to calculate the Fourier transform of signum t, right? So in this example, we are trying to calculate the Fourier transform of signum t, right? So my signal is SGM t, right? And what does this look like? This looks like this. Okay, right. That's signum t, and the definition I told you in the last class is that it gives you the sign or signum of the function, right? This gives you, so this is signum t, right? Right. So this gives you this. So this gives you a value of -1 if t is less than 0. This gives you a value of +1 if t is greater than 0, and this gives you a value of 0 if t is equal to 0. All right. All right, with that said, we are trying to calculate the Fourier transform of this. So one of you actually were able to calculate this, I mean, for the most part, and send me the answer. Okay, so again, for this particular problem, we could technically, let's try to do that. from our definition, right? So let's calculate the Fourier transform, right? So we are calculating x omega, right? And that's this integration, right? And again, if you have any query, any problem understanding what I'm saying here, please feel free to ask. Okay, so function is SGNT, that's the signum function. So we are calculating the Fourier transform here, right? So with that said, we have to split this integration into two portions, one from minus infinity to 0, where so basically when t is negative, and when, yeah, you want to know the answer, right? When, and for one for plus 0 to plus infinity when t is greater than 0, right? So we have to consider these two situations. So one integration from minus infinity to 0. So this is basically the condition when t is negative. So this is SGNT into e to the power minus j omega t, and this is plus integration from 0 to infinity SGNT. Yeah, it will be like the Fourier transform of 1, except for one very important thing. We shall see. Except for one very important thing here. E to the power minus j omega t dt. Okay, there is one more thing. If you write something wrong, okay, don't retract your message. It does not matter if you write something wrong. Unless you are writing something like a slang, then retract your message. Yes. Let's see how we can proceed with this, right? Okay. So if we have that, okay, if we have that and deal with it like that, we have a situation, we have a particular problem. What particular problem do I have? Okay, the particular problem that we might encounter is that while putting the limits, we would have a difficulty, right? So let's do that. So we have a minus sign here, right? We have a minus sign. So what do I have as a when discussing this? What do I have? While discussing this, what is the problem that we might encounter? Of course, that's a minus sign, right? So minus 1, right? Within this limit. So this is the integration from this and this, minus 1 e to the power minus j omega t, right? And dt, and plus, so we have integration from minus infinity to 0, right? So we have plus 1 into e to the power minus j omega t and dt, right? So let's try putting the limits here. Let's try putting what am I writing? That's going to be 0, right? Okay, let's try put in the limits. Okay, let's see what we really encounter, for example, here, right? Let's try to figure that out for ourselves. Now often what happens is we often cannot always get away by doing some tricky mathematics, right? But sometimes we can, and here probably we would be getting away with some tricky mathematics here. Okay, let's see what I'm talking about here. Okay, so this minus sign is there, and let's integrate that. And if I integrate that, I would have e to the power minus j omega t, and I have a minus j omega down here, and we have a minus sign, so we have j omega, and the lower limit is minus infinity, upper limit is 0. Okay, like that. And plus here, if we have this e to the power minus j omega t by minus j omega and 0 and infinity, right? So we can have this kind of expression here, right? We can have this kind of expression here. But try to understand something very important here. If I put the limits here, again, we are encountering a similar situation like we had earlier, right? We are encountering a similar situation like we had earlier, where if I put minus, so if I put the upper limit, of course, on the upper limit I have e to the power 0, right? If I put t equal to 0 on the upper limit, I have e to the power 0. So that's 1 by j omega, right? And with a minus sign, if I put negative infinity here, okay, negative infinity here, I would have e to the power j omega t and something like that. But unfortunately, since I have negative infinity here, Okay, we have a problem then at that particular point. What is the problem? We have a situation where we cannot discern the limit properly, right? We cannot discern the limit properly, right? So we cannot discern the limit properly. So with that said, we don't really know what to do right now with that information. So is that clear? Okay, so with that, what we can do, we can say that up to this point is fine, right? But if I put this limit here, we have a problem. What problem do I have? I have a situation where I am encountering a situation where my values are so basically this e to the power minus j omega t, that's cos omega t minus j sine omega t. So this is bounded between +1 plus j, -1 minus j. But if I put infinity, I'm not entirely sure what the value is, right? So it does not converge. So calculating the limit will be impossible because after this, I cannot proceed without breaking mathematics, right? So without breaking mathematics, I cannot proceed. So let's break mathematics here. Okay. So after this point, we cannot actually proceed without breaking mathematics. So let's try not to do that. Okay. Let's try drawing the signal once more. Let me draw the signal once more, and let me give you a simple insight about the signal. Okay. Instead of saying some ad hoc things here, let's try doing something important. Now notice this. I did all this just to tell you that this is not how it works. Okay. Now notice. Okay. Notice this. Okay, sorry. Okay. Let's draw the signal we have here. And again, I don't want to really, I don't want to break mathematics, right? I don't want to say something ad hoc here, and yes, and try to get away with that. I mean, many of us really do, since we are engineers after all. If we say something wrong about mathematics, it does not, no one really would care. So yeah. So say we have a signal like that, right? We have a signal like that, but try to look at this. Okay, try to look at this, and let me tell you, and let's say that we are trying to figure out the Fourier transform of this, but we have a problem with this, right? Because we could not integrate this. This is -1, so this is 0, right? We could not integrate this, right? We could not, right? So now instead of that, let me ask you to find out the Fourier transform of something slightly different. Okay, what's slightly different? Now I'm asking you to calculate the Fourier transform of a signal that looks like this. Let me draw that here. Okay, I'm asking you to calculate the Fourier transform of a signal that looks like this. Okay, again, it's a bad drawing, right? Okay. Okay. So let's calculate the Fourier transform of something that looks like this. And my question is, what is the function? What is the signal that looks like this? Okay. So of course, here for this portion, what is the signal? So this is e to the power minus t, or rather e to the power minus at, right? Right. That's e to the power minus at. And what is this signal? Can anybody shed some light on this? What is this signal? What is this signal? So I am trying to calculate the Fourier transform of a signal that kind of looks like this. Okay, so kind of looks like this. So here this portion is e to the power minus at. So what is this portion? Okay, can anybody tell me? Because I want you to figure that out. Figure this out. So this is e to the power minus at. You already know that. And this portion, what is this portion? Can anybody tell me? All right. So I'm writing something here. I'm going to write something here. Okay. So tell me about a signal that decays like that, starts with a value of -1. Okay, not minus e to the power minus 80, but minus e to the power 80. That's going to be minus e to the power 80, right? Right? T is a negative quantity. Of course, when t becomes minus infinity, this becomes 0. And a is a positive quantity, of course. Okay. So since t is negative in this direction, I have e to the power 80, not minus 80, and minus sign, of course. Yeah, minus e to the power 80, right? Minus e to the power 80. So that is something you understand, right? So let's now try to calculate the Fourier transform of this, okay? So that we don't have to break mathematics for us, okay? Let's not break mathematics for us, and let's try to calculate the Fourier transform of this instead, right? Okay, let's calculate the Fourier transform of this instead. So instead of breaking mathematics, let's calculate the Fourier transform. So let's calculate this. So my signal here is like this. The signal has a value of minus e to the power 80 when t is negative. It has a value of e to the power minus 80, so plus e to the power minus 80 when t is positive, and it has a value of 0 while t is equal to 0. So taken together, this signal is mod e to the power hold on. Okay, let's forget that. Okay, let's define this way. Let's not complicate unnecessarily, right? So let's calculate the Fourier transform of that. So what is x omega? What is x omega? X omega is, of course, integration from minus infinity to infinity. So we have xt e to the power minus j omega t. We are calculating the Fourier transform. So again, this function is defined in a piecewise fashion, and again here look carefully, a is greater than 0. Okay, so let's do that. Let's split this integration from minus infinity to 0 for negative t's. Okay, right there, and for positive values of t. Okay, so now here when t is negative, what is the value of the function? It is e to the power, what was it, minus e to the power 80, right? Minus e to the power 80 when t is negative, right? And try to now understand a is a real number, so I can now happily deal with the limits, and this is 0 to infinity, and here xt. Now, for example, t is positive here right now, so this is going to be e to the power minus 80, and we have e to the power minus j omega t dt. This integration is going to work now, right? So of course now let's okay, let's write one more line. So minus infinity to 0. So this is going to be minus. Okay, let's check the minus sign outside. This is e to the power a minus j omega t dt, plus this is integration from 0 to infinity e to the power. Again, if you have any query, anything, if there is anything you cannot follow here, please ask me. Right, okay, ran out of pages here. All right, so here we're now trying to put the limits here, right? So minus, now here let's integrate this. That's going to be e to the power a minus j omega t divided by a minus j omega, and the limits are minus infinity to 0, plus here I have e to the power minus a plus j omega t divided by minus a plus j omega and 0 to infinity. So we have that, right? And now try to see that when I do this, okay, let's think about the infinity limit for this particular example. Okay, let me show you how that infinity limit works here. Okay, so when I put the infinity limit, for example, limit for this lower limit for this particular scenario, okay, for this particular scenario, what is the lower limit? So try to understand that for this particular scenario, the lower limit is kind of like this, limit t tending to minus infinity, and let's forget about this. Okay, let's forget about a minus j omega, let's forget about that. Let's just think about this, e to the power a minus j omega t, right? Let's think about that. So we are actually calculating this limit, right? So with that said, limit t tending to minus infinity, that's the lower limit for this first portion, right? And let's see, let me show you, we are not breaking mathematics, right? So it is e to the power at into e to the power minus j omega t, right? And we did this actually in an earlier class to show you that this is completely okay to do. So this is e to the power at, we call a is a real number, and e to the power minus j omega t is cos omega t minus j sine omega t. Now this quantity is bounded between plus 1 plus j minus 1 minus j, right? So this automatically jumps between those. This can never go to infinity, right? Something like that. Okay, this is a bounded quantity. Bounded between minus 1 minus j and plus 1 plus j, right? This is bounded between these two numbers, right? Of course, because sine and cosine, they are bounded between plus 1 minus 1. Now what happens to this? If I put the limit here, recall that a, in our example, a was greater than 0, right? A was greater than 0, right? So a is a positive quantity. So if I put negative infinity on top, so I have e to the power negative infinity, because t is negative infinity, I am multiplying that with a positive number, so e to the power negative infinity, right? So because of that, this goes to 0, because this is a finite quantity. Finite means bounded between two finite values, and this goes to 0 because this goes to 0, right? This is actually going to 0. This is because this is going to go to 0, because simply that a is positive, t is negative infinity, so I have e to the power negative infinity, so this is going to 0. Similarly, for this scenario here, I have e to the power minus at, and t is positive infinity, right? Because of the same idea here, okay, because of the same idea here, I have e to the power minus at and t is positive infinity, so we have e to the power negative infinity. Okay, that's also a 0. So the lower limit here is 0 and the upper limit here is 0 for this particular example, since a is a real number and positive real number, but as a matter of fact. Okay, so let's bring this down in size. Okay, as a side note. Okay, and so this is minus, let's put the upper limit. If I put the upper limit, this is going to be a minus j omega, and when you put the lower limit, that's a 0, plus, think about this one, when you put the upper limit, that's a 0, and when you put the lower limit, so that's the numerator is 1, so 1 by minus a plus j omega. So we have that, right? We have that. There is no problem with that, right? I believe. So what do I have? I have minus 1 by a minus j omega and plus 1 by a plus j omega, right? Right. So do tell me if I don't think I have made any mistake here. I hope, really. So with that said, if I write down in a proper fashion, so on the denominator I have a So that's a square, sorry, that's a square minus so a square minus j square omega square, so a square plus omega square, and on the numerator I have a minus j omega minus a minus j omega, so minus 2 j omega, right? All right, so what have we discovered? Therefore we have discovered that the Fourier transform of this signal, this blue one, okay, let me copy and paste this. Therefore we have discovered that the Fourier transform of this blue signal, this purple one, okay, which was defined in this way, okay, has a Fourier transform of this. The Fourier transform of that signal is this minus 2 j omega by a square plus omega square. That's minus 2 j omega by a square plus omega square, right? The Fourier transform of this particular signal is this. What am I doing again? I am trying to calculate the Fourier transform of the signum function, right? Fourier transform of the signum function. Now let's consider a very nice situation here. What if I have this figure, right? What if I have this figure here and try to understand the fact that what happens with this definition what happens when a tends to 0? When a tends to 0, what happens then? Do tell me that. So 0 plus, a very small positive real number. What happens when a is a very small positive real number? What happens then? Right? What happens then? Right? This is the slope. This is how fast the signal decays. Right? If a is smaller, okay, the decay will slow down. Right? The decay will slow down. Then what happens to the signal? What happens to the definition? Try to understand. Definition was e to the power minus at when t was less than 0. But what if a is a very small quantity, very small positive quantity? If it's a very small positive quantity, so small that it's very close to 0, then what happens? This is plus 1. Sorry, this is minus 1, right? This was this was minus e to the power at. What happens when a is a very small quantity? When a is a very small quantity, when this limit is applicable, this essentially becomes minus 1. Okay, we are proceeding from this definition, right? So when t is and now for example when t is greater than 0, this signal had a value of plus e to the power minus at. But what if a is a very small quantity? If a is a very small quantity, then this becomes 1 because it becomes e to the power 0. So this is a plus 1. And of course we knew that when t is equal to 0, this signal has a value of 0. So I can now say that this signal here, okay, this signal here approaches, so the purple signal approaches a signum. Signum means SGN, okay, signum when a tends to 0. So when a is a very small quantity, this signal eventually approaches this signum function, right? Because if a is a smaller quantity, if a is smaller, what happens is the slope will be even higher. Okay, if a is even smaller, the slope will be even higher, and so on, and eventually this will merge with this, of course. So this definition tends to this definition when a is a very small quantity. So with that limit in mind, we knew that the Fourier transform of this signal was this. Then question is, what would be the Fourier transform of the signum function? Of course, understandably, the Fourier transform of the signum function would be this when a tends to 0, right? So therefore, Therefore, the Fourier transform of signum function SGNT would be limit a tending to 0 plus, which is a very small positive real number, okay, on this minus 2j omega by a square plus omega square, right? Because the signal for which we calculated this as the Fourier transform was this, right? And now if I take a tending to 0 here, that becomes a signum function. So similarly, whatever I do on the left hand side for a Fourier transform, okay, the same thing I should do on the right hand side because of the linearity property, okay. So if that is the function for which the Fourier transform is this, then if I take a limit a tending to 0 here, I should also take a limit a tending to 0 here. And if I take a limit a tending to 0 here, this signal becomes the signum function, a signum signal, okay. So obviously, if I have to take the limit a tending to 0 here. So if I do that, what do I get? A tending to 0 essentially gives you 0 here. So that's right. So I have minus 2j omega by omega square, right? But what is omega square? What omega square is minus, so minus j square omega square. Of course, minus j square is plus 1, j square is minus 1. So minus 2j omega. So I can cancel 1j out. So I would have 2, and on omega out also 2 by j omega. So 2 by j omega is the Fourier transform of the signum function. Therefore, Fourier transform of signum function without breaking mathematics would be 2 by j omega. Try to see, we did not break mathematics here, right? We did calculate everything as a limiting function of something else. And here, if we could, if I proceeded from here, okay, I would have broken mathematics in some way or the other. Here, this is the Fourier transform of the signum function. So please let me know if you understood this huge discussion here right now. All right. So with that said, so this is xt and this is x omega, right? So what is mod x omega? So the amplitude, that's going to be mod of 2 by j omega and that's going to be 2 by mod j omega. That's going to be 2 by root over yeah, way too huge, right? So correct ways are often way too complicated, but that's the correct way unless you want to dive into complex integrations. So that's what it is, right? This is not 2 by omega, this is 2 by mod omega, right? Square root of a square quantity is the modulus, so you cannot write just omega here, right? So that's the amplitude spectrum. So if I now plot the amplitude spectrum for the signum function, okay, again let me pull back the signal. So okay, so yeah, that is why, I mean, you have to practice these things a lot, okay? I did not learn these things in a day, so you should also expect to learn these things in a day, right? So you have to practice a lot, and we shall get quite a few practical problems to deal using these things. So that's the signal, right? That's a signum signal, right? So this is SGNT, so this is +1, this is -1, and that's a 0, right? So that's how the signal jumps in the shows up in the time domain, right? So this starts from -1, goes up to +1, and so on, right? So what is it in the frequency domain? What is the amplitude spectrum, right? At least the amplitude spectrum. So this is omega. What frequency components does it have? So the signal had a value of -1, and at t equal to 0, the signal jumps to a value of +1, right? So this is the amplitude spectrum. And if I look at this is kind of a rectangular hyperbola, but not really. Okay, when t is positive, so this can be again written as this. This is 2 by minus omega when omega is less than 0, and this is 2 by omega when omega is positive, right? Right. So with that said, if I draw the signal, draw the amplitude spectrum of the signal, then we end up having something like this. That's kind of the value of omega square instead of cancelling omega. What? Why did I write omega square? Here, are you talking about omega square here? Okay, if you're saying I'm writing omega square here instead of cancelling omega, yeah, I did cancel omega, right? I did cancel omega, right? I did cancel one of the omegas, right? When I got the chance to, right? I did cancel one of the omegas. But here, I cannot just write omega because taking a square root of over a square does not give you omega, right? Just to show you that. So I'm saying the square root of x square is mod x. Why? If that's your question, this is the answer, right? So x is, for example, say 5. If x is 5, so for example, then what is x square? It's 25, right? Then what is the square root of x square? Yeah, what is the square root of x square? That's 5. And don't say plus minus 5, because I don't have a plus minus sign here. Whatever sign I have here is the sign, right? So that's plus 5, right? Very carefully, plus 5. Similarly, if I give you x equal to minus 5, what is x square? That's 25. What is square root of x square? That's again plus 5. So this function itself, taking a square and then a square root, appears to be a simple modulus operation, right? It's getting rid of the minus sign. Even if I give it a minus 5, this gives me a plus 5. If I give it a plus 5, it gives me a plus 5, and so on, right? I think that was your question, right? That's why, I mean, taking a square root over a square quantity is not just that particular quantity. It's a modulus of that quantity. Right? I think you got that, right? Okay, minus 2 j omega by omega square. Yeah, I did cancel omega, right? I did cancel omega. Why are you saying? You're saying the part by 2 j omega by omega square. I did cancel omega square. I did write like that. Of course, I did that. Okay, from here to here. Oh no, that's not an issue, right? From here to here, I did not cancel omega. Okay, I did not cancel omega because whatever, you can, right? You can. Right, you can cancel omega here, right at this point you can cancel omega. You would still end up with this answer, right? Right? My point is simply that j square is minus 1, right? That's the entire point, right? You can write minus 2j omega by omega square. On the next line, you can write minus 2j by omega, and then try to understand the fact that j square is minus 1, right? You understand that, right? So minus j square is equal to 1, right? So what is this? This is, now we have cancelled omega here, right? Happily, we have cancelled omega. So now we have omega here. So can I write minus j, what am I doing? Can I write this minus j square omega? Of course I can, right? Because minus j square is nothing but plus 1, right? Right? This is plus 1, so this is just omega, right? So I can cancel out the minus signs here. I can cancel out 1j here. So I essentially have the same thing, right? Same thing here, right? So that would end up being a small additional calculation to show you. So you can always trace back to this. Right. So I believe you got up to the end of this, right? So we are actually plotting the frequency response or the amplitude spectrum of this, right? So this was kind of a rectangular hyperbola, but instead it has kind of a formation like that. Okay, rectangular hyperbola. For rectangular hyperbola, these are the asymptotes, right? Yes, the thing is, as long as whatever you do is mathematically correct, no one can question what you are doing. That's true for you as a student, that's true for you as a teacher as well. So right, so that's the amplitude spectrum for this, right? So that's the amplitude spectrum. But my point is, what does this tell you? But my question is, what does this tell you, right? Earlier, I asked one of you. Now, if I ask you this, for this particular signal, this is the amplitude spectrum, right? So these are the different amplitudes of different frequency components present in it. My question is, what is x0? So DC component, if I ask you, what is the DC component? What is the DC component in signum t? Okay, so what is the DC component in signum t? Of course, what is the DC component? It's the zero frequency component, right? X0. So x omega, so x0, right? But what is that? So what is the value of x omega when omega is 0? Right? To tell me that. What is the DC component present in this signal? What is the amplitude of the DC component? Right? What is the amplitude of this? 1? Why is it 1? Why do you think it is 1? Here, put omega equal to 0. What do you get? Here, if you put omega equal to 0, what do you really get? Yeah, that's infinity, right? That's my point. So for this signal, the DC component is going to infinity. But as electrical engineers, can any one of you tell me what is the significance of a DC component that's infinite? What is the significance of this? But what does it mean? What does it mean to have an infinite DC component present in the signal? Right. What does it mean to have an infinite DC component present in a signal? Can anybody shed some light on that? Okay, I would leave that to you to ponder upon later on. Okay. So instead of so yes, this is my question, right? So try to figure out what does having an infinite DC component mean? Would really mean. What are the implications of that? Okay. Instead of saying what it means, don't answer me mathematically. Okay. Give me an answer as an electrical engineer. Okay. What does it mean to have a signal that has an infinite DC component? Okay. No, infinite DC component. The amplitude of the DC component is infinite. That is what it means. The amplitude of the constituent DC component, okay, is infinite. Okay. So what does that mean? Okay. Instead of saying what is the amplitude, I'll say. My question would probably actually be, what is the amplitude of the, right? And let's say this, that's the amplitude of the DC. Now I think it's clear, right? What I'm trying to talk about here. So the amplitude of the DC component even supposedly is infinite. Right. All right. Right. So we are going to do that later on. I don't have enough time today, so we shall do that later on. So let's solve the 10th problem. And we are ending our discussion with, we started our discussion with Dirac delta, the impulse, and our discussion with the unit step, right? What is xt? Xt is unit step. Now we are trying to find out the Fourier transform of that. Again, this will be like a homework for you to, figure this out as an electrical engineer. What it means to have a signal that has infinite DC component. Okay, DC component of infinite amplitude. In any case, let's think about UT. What is UT? Okay, UT is this signal. Right? We're trying to find out the Fourier transform of this, because again, this is one of those signals for which if I try to find out the Fourier transform in the conventional way by doing an integration, we would be entirely at a loss. Okay, so this is a unit step. All of you know that already, right? So before I can actually solve anything, let's try to figure this out by ourselves. All right, so that's like that, right? So do tell me if you don't understand this. Right. All right. All right. So now that's UT. Instead of saying XT, let's say this is UT, right? No problem with this, right? So now let me ask you this. Yeah, if one of you are saying that the DC component infinity means it would appear to be a short circuit. Okay, yeah, not necessarily so, but you are close. Try to think. You are close. You are kind of close, right? This is 2UT, right? This is 2UT. Is there any problem with this? This is 2UT, right? This is UT. This is 2UT, and you will shortly know where I am going with this. Right? This is 2UT. Right? Any problem? No. Right? Now, with that knowledge, let me draw 2UT minus 1. So of course you know already that 2UT minus 1 would be a downshift for this signal by 1 amplitude, right? By 1 unit downshift, right? So if I take this signal and downshift it by 1 unit in order to get 2UT minus 1, what do I really get? What do I really get? This is nothing but the signum signal, right? This is minus 1, this is plus 1. So this is 2UT minus 1, right? So this is UT, this is UT, this is 2UT, and this is 2UT minus 1. Right? So here now we can say, but we know that 2UT minus 1 is equal to signum T, right? That is 2UT is signum T plus 1, right? So UT is nothing but signum t plus 1 divided by 2. Right? So with that knowledge, I can now say the Fourier transform of ut is nothing but the Fourier transform of signum t plus 1 divided by 2. Right? So that's equal to the Fourier, so that's equal to half into Fourier transform of signum t plus Fourier transform of 1. Right? Half. So now we already calculated the Fourier transform. We already calculated the Fourier transform of signum t. This was 2 by j omega. Okay. And we also calculated the Fourier transform of 1, that was 2 pi delta omega. Right? All right. All right. So if we now, of course, if we try to put a modulus sign here and calculate everything, calculate the mod of the complex number here. Okay. So of course, this will be 2 by mod omega and a delta. So if I do plot the amplitude spectrum here, okay, the amplitude spectrum is kind of going to look like that, right? It's kind of going to look like, so let's simplify this, 1 by j omega plus pi delta omega. This is kind of going to look like this one, right? Going to look like this one. That's the spectrum. But along with that, so that's like 1 by j omega, right? So modulus of that. So along with that, we have this component pi delta omega. So if I draw that, that comes in addition to this, right? So along with that, we have an impulse here. So this is the Fourier transform for this signal. So we have an impulse here. We have an impulse, okay, and this. I think you got that point, right? So if somebody asks you, what is the DC component present in unit step? What is the question? What is the answer? So what is the DC component present in unit step? So here for this example, so DC component would be x0. Would be x0. What is x0? That's pi delta omega, right? And omega is 0 here, so pi delta 0. That's the DC component here. So now this kind of has a finite answer, for example, right? Okay, definite answer, for example. We know something happens here. Okay. So the DC component itself is an impulse. Yeah. Okay. So this is the amplitude or area under that. Okay. So this has a finite DC component per se. Okay. But the signal does not. So with that said, we are going to discuss, we are already way over time. So we are going to end our discussion today with the declaration that we are going to do that problem later on for that particular pulse signal. No, you cannot calculate the Fourier transform ut by definition. You would encounter the same problem as we did with this. If you try to calculate the Fourier transform ut by definition, okay, you would encounter the same problem as we did with this. Okay. So yeah, ut by definition would be somewhat like this, right? This portion would be 0. This portion would be 1. When t is greater than 0, this portion would be 1, right? If you calculate the Fourier transform of ut by definition, this is going to be 0, that's going to be 1. So that's going to be 1, right? So that's the definition. So 0 to infinity, integrate over this, right? So the problem is, again, you're going to calculate this limit, and the moment you put infinity on top, same problem, because this is going to be cos omega t minus j sin omega t. Okay, it does not matter what is the value of t you put there, it does not converge if t is infinity here, right? It does not converge, right? Same problem, right? If you calculate the Fourier transform of ut by definition, you are going to just do this integration and you are going to end up with the same problem with the limits. Okay, I think I hope I cleared that up, right? Right. So this is the only way, rather, this is the only one of the few ways in which we can tackle these problems. And this is literally the only way through which we can actually avoid complex integrations. Okay, avoid complex analysis. So yeah, if I introduce complex analysis here, it will be very difficult for you to actually do anything with it. With that said, we shall solve, we have one more problem left. Okay, and again, your homework problem today would be this. Your homework problem today, where is it? Yeah, to calculate the Fourier transform of this and give me an explanation, right? You would encounter something of this type, something of this category, while calculating the Fourier transform of sine omega naught t. And I would encourage you to actually solve that and plot that and let me know what you think. Okay, write down an explanation of what you see, right? With that said, if you have any query, please let me know. Otherwise, we're going to end the stream right now. And we shall send, of course, as usual, I shall send you the handouts. So no worries about that. So please tell me if you have any query. Okay. So if you have any query, please let me know. I'll be here for two more minutes. Alright, try solving the problem then and send me the answer. Just take a photo, take a snapshot of that and email it to me. In any case, that will be the end of today's class. So we shall have our next class on Wednesday, and there we shall actually start by solving that particular problem, and then we shall look into different properties of Fourier transform, because for our many of our practical problems we would encounter while discussing system or analyzing systems and how they interact with signals, we shall have to use different properties of Fourier transforms, right? So we shall learn those. In any case, that will be the end of today's discussion. So if you have any query, if you encounter any query down the line, you can always drop me an email. I shall respond to your email. Don't worry. Thank you very much. So that will be the end of today's class.